Section 5.5, Counting Techniques. We'll look at these three objectives in this section. Objective 1, we want to solve counting problems using the multiplication rule. The multiplication rule of counting says, if a task consists of a sequence of choices in which there are P selections for the first choice, Q selections for the second choice, R selections for the third choice, and so on, then the task of making these selections can be done in P times Q times R and so on different ways. So in this example, we'll count the number of possible meals. For each choice of appetizer, we have 4 choices of entree, and for each of these 2 times 4 equals 8 pairings, there are 2 choices for dessert, which is a total of 2 times 4 times then 2 for the desserts, which will give us 16 different meals that can be ordered. If n greater than or equal to 0 is an integer, the factorial symbol, n with an exclamation point, is defined as follows. N factorial is equal to n times n minus 1, and so on going downward, times 3 times 2 times 1. 0 factorial is equal to 1, and 1 factorial is equal to 1. Those are 2 special factorials. Objective 2. We want to solve counting problems using permutations. A permutation is an ordered arrangement in which R objects are chosen from n distinct or different objects, and repetition is not allowed. The symbol NPR represents the number of permutations of R objects selected from n objects. So our number of permutations of n distinct objects taken R at a time. The number of arrangements of our R objects chosen from n objects in which 1. The n objects are distinct, 2. Repetition of objects is not allowed, and 3. The order is important. And that's the key here with permutations, that order definitely matters. It's given by this formula. NPR is equal to n factorial divided by n minus r factorial. In this example, we want to look at betting on the trifecta. In how many ways can horses in a 10-horse race finish first, second, and third? The 10 horses are distinct. Once a horse crosses the finish line, that horse will not cross the finish line again, and in a race, order is important. We have a permutation then of 10 objects taken 3 at a time. The top 3 horses can finish a 10-horse race in 10, choose 3 ways. So that would be equal to then 10 factorial divided by 10 minus 3 factorial. Or 10 factorial divided by 7 factorial. Remember with factorial that we're multiplying each digit by the ones below it. So we have 10 times 9 times 8 times 7 factorial divided by 7 factorial. Now technically I could have continued on to do 7 times 6 times 5 times 4 times 3 times 2 times 1. But notice that I have 7 factorial in the numerator and 7 factorial in the denominator. Because I'm multiplying, I can then cancel these 2 values, and I end up with then just 10 times 9 times 8, or 720 ways. Objective 3. We want to solve counting problems using combinations. A combination is a collection without regard to order, so in this case order does not matter at all, of n distinct objects without repetition. The symbol NCR represents the number of combinations of n distinct objects taken R at a time. So our number of combinations of n distinct objects taken r at a time says the number of different arrangements of r objects chosen from n objects, in which number 1, the n objects are distinct, 2, repetition of objects is not allowed, and 3, order is not important. And again, that's the key for combinations, that order doesn't matter. It's given by this formula. NCR is equal to n factorial divided by the quantity r factorial times n minus r factorial. So let's look at an example of simple random samples. How many different simple random samples of size 4 can be obtained from a population whose size is 20? The 20 individuals in the population are distinct. In addition, the order in which individuals are selected is unimportant. Thus, the number of simple random samples of size 4 from a population of size 20 is a combination of 20 objects taken 4 at a time. So we'll use our second formula for combinations with n equal 20 and r equal 4. So we have 20C4, which is equal to 20 factorial divided by 4 factorial multiplied then by 20 minus 4 factorial. So we have 20 factorial divided by 4 factorial times 16 factorial. So we have 20 times 19 times 18 times 17 times 16 factorial divided by 4 times 3 times 2 times 1 times 16 factorial. Now we can again cancel our 16 factorial since everything is being multiplied. And in the top, the remaining values we will get 116,280 divided by 24, which will give us 4,845. So there are 4,845 different simple random samples of size 4 from our population whose size is 20. So let's look at our technology step-by-step for factorials, permutations, and combinations. First, we'll look at factorials. So to compute 7 factorial, we type 7 first on the home screen. Then we press the math button and arrow over until PRB is highlighted. Then we will select number 4, which had our factorial symbol. Now with 7 factorial on the home screen, we press enter again and see that we get a value of 5,040. Now let's look at technology step-by-step for permutations and combinations. To compute 7P3, or a permutation of 7 objects taken 3 at a time, the first step is to type the 7 on the home screen. Then we press the math button, arrow over to PRB to highlight it, and then select number 2 for NPR. Now we type a 3 on the home screen and we press enter. And we see that our permutation of 7 objects taken 3 at a time was 210. Note, to compute 7C3, or a combination, we're going to select the number 3 instead. So we'll do the similar steps. We'll type the 7, press math, arrow over to PRB, and now we'll choose number 3. And then we type in the number 3 for our R value and hit enter. And we see that for the number of combinations of 7 objects taken 3 at a time, we only get 35.